Hello, today I'd like to speak a bit about big O notation. Probably many of you already came across this term. It sounds a bit mysterious, but it's quite simple to understand if you have some mathematical background. Having said that, let's try to define what big O notation is. So simply, it is the way for describing efficiency of some solution regardless of the environment where it is on which it's running. So it might be running on computer which is very fast, but it might run on very slow simple desktop, for example, and we don't care where it is running. We just want to know how our time needed to execute this solution will evolve along with input data size. So having said that, let's try to draw some very common functions representing complexity in big O notation. So the first and very obvious is O1. This is the best case that probably we would like to always achieve when we implement something, but it's very rarely possible. So this function simply means that regardless of our input data size, for example 1000, 1 million, million of millions elements, we will have a constant execution time, which for example might be 2 milliseconds every time. So this is possible when it comes to very simple things like accessing for example first element in an array, or accessing some element in a hash map if it's not a degenerated hash map. So we can roughly assume that execution time of that simple thing is constant and only depends on the memory or CPU speed. Yeah. So this is the most happy case, and we call it O1. Very rarely possible to achieve when it comes to some more complicated problems. Okay, the next one, very popular as a linear complexity or proportional complexity. So the function, as you probably expect, is like this. We call it On, where n usually refers to our input data size, yeah, the problem size. So this simply means that our time needed to solve some problem will grow proportionally to the input data size. So if we have, for example, 1000 of elements in our array, the program will execute in 1000 milliseconds. If you have just one element, it will be 1 millisecond. So it's proportional. It's not the very best complexity when it comes to some solutions, but sometimes it might be acceptable. So the example of such complexity might refer to a problem where we, for example, want to count odd or even elements in an array. So this will be linear because if we have 100 elements in our array, we have to visit each of them in order to detect whether the element is odd or even. So the time will grow proportionally. Yeah. Another popular complexity that you might heard of is square complexity. Square complexity is something like that. We call it On square. So it's kind of a square function. So we simply see that this function is much more sensitive to input data size than the previous one. So if we change our data by, for example, if we have 2 elements, we will have 4 seconds time, for example, not like 2 seconds time in this case. Yeah. So for 2 elements, if we have 2 here, so it should be like this, 4. So for this exponential, it is 4 seconds. Square, it's 4 seconds. For this linear, it is just one. It's 2 seconds. Yeah. So the difference when it comes to small data size, it's not that big. It might have a not very big meaning for us, but when it comes to big data structure, it really matters. So we would like to avoid such a complexity when we implement something. So the example for square complexity might refer to a problem when we want to sort some array of numbers, and we use a bubble sort algorithm. So in the worst case, when we have already reverse sorted array, like it will be, for example, in descending order, and we want to sort it in ascending order, the execution time will be proportional to the square of number of elements. Yeah, so it's not very good. Okay, another much worse complexity, which we for sure would like to avoid and don't apply to any solution, is exponential complexity, which is extremely sensitive to input data size. We call it O2n, where, for example, 2 is some constant that we want to apply our exponent to it. Exponent will represent input data size, so it will grow much faster than square, and much more faster than proportional complexity. Okay, the third complexity that I would like to speak about, and very popular, is the logarithmic complexity. It's sometimes our goal to achieve such complexity when we implement some algorithm. So algorithm is that kind of shape. This is O log n. And this complexity is quite acceptable, because we see it's a bit sensitive to change of input data size, where this data is quite small, but it's very little sensitive. It's not much sensitive when it comes to big data size. So it's sometimes we call that our senses has a logarithmic characteristic, because if we hear something, it is loud, we don't notice any difference if it is two times louder. Yeah, so that's why we apply decibel scale for for describing sounds. Yeah, let's move on. So logarithmic complexity, to which problem it could apply. Logarithmic complexity we can achieve when we want to search a binary tree which is balanced, yeah, or if we want to search for some name in a phone book, and we use an approach where we branch a book into 2 parts and see whether our element, what we are looking for, is on the on the left side, on the right side, alphabetically. So if it's not on the right side, if it's on the left side, then we branch left side on 2 pieces, and so on and so on. And that kind of approach has logarithmic complexity, which probably the best way to understand that is to analyze some real code examples. So then you get a better feeling what they means. So as usually, I put in a comment my link to my GitHub, where you can find a project with some examples of those complexities in big O notation. There you can find functions and Spock tests that will prove that the complexity is logarithmic, proportional, square, or exponential for some problems. Thank you.